Our next speaker will be Rachel Friesen, and I'll let her start to set up here. And the title of her talk is Beyond Ammonia, 3 millimeter line surveys of molecular clouds with Argus 144. Are you ready, Rachel?
Yep, just getting things set up here.
We can see your screen and carry you just fine. There.
Okay, so you can see my presentation fine?
Yep, it looks great.
Wonderful, thank you very much. And thanks to the previous speakers who have provided some really nice introduction to star formation and what we're looking for in terms of some ideas of surveys with Argus 144. So my presentation today is going to be talking about 3 millimeter line surveys of molecular clouds in our galaxy with Argus 144, with the caveat that going beyond ammonia. So I am going to talk about ammonia because ammonia is near and dear to my heart. But what I'm going to hopefully show is how some of the large surveys that we've done with the GBT, with the Green Bank Ammonia Survey and the Keystone Survey in particular, kind of laid groundwork for what we can do with Argus 144. So I'll just have a kind of a brief introduction because we've had some really nice talks already by Che Yu in particular, starting off with what we're looking for in terms of what questions are we asking for star formation in nearby clouds. So in our local galactic environment, we find a large range of star formation activity between, for example, regions like the Taurus molecular cloud, shown on the left in Herschel dust continuum imaging, that's forming a smaller, low mass, more distributed stellar population. And then regions like Orion that contain much more gas at higher densities and are forming high mass stars and associated denser stellar groups and clusters. So these large continuum surveys, in particular Herschel observations in the past decade or so, have really shown the overall structure of these molecular clouds, how filamentary they are. Which, you know, we have known about filaments in molecular clouds for a long time, but this ubiquitousness of filaments has been something that really came to light with the Herschel data. And in addition to that, what we notice is that star-forming cores are primarily found within these dense filamentary structures. And so in the past several years, there's really been a lot of work to create surveys that build on these continuum observations to provide the kinematic information that's missing from the continuum in order to really assess, you know, kind of the physics, the stability, the dynamics of clouds like regions like Taurus, regions like Orion, and even going further distant into the high mass star forming regions that might be somewhere, you know, kiloparsecs away in our galaxy. So some open questions, you know, there's lots of things that, you know, people are interested in terms of looking at the physics of star formation. But some of these open questions that I'd like to highlight are very generally like, how do filaments fragment into cores? How do we find form cores in filaments? And how do they then become gravitationally unstable and collapse? Something that she already talked about, how does the angular momentum of structures evolve from large to small scales? Does it follow a simple picture, or is there a lot of influence from the turbulence in the region, which we can then map by looking at tracers of different physical environments, different tracers to trace the different environments within the clouds? How do magnetic fields impact the evolution of star-forming cores? How does collapse proceed once the core becomes gravitationally unstable? And more generally, how do we keep star formation efficiency low on average in molecular clouds? So we have a wealth of data coming in, especially in the past few years with some of these surveys, but you know, we still have many unanswered questions. So to start off with talking about ammonia, I really wanted to highlight what the transition from moving from having a single pixel in the K-band to the K-band focal plane array, how much it dramatically increased our ability to survey star-forming clouds in lines like ammonia. So on the left, I'm just showing you the beam pattern of the KFPA. And kind of going from left to right, you know, we started, I would say, many researchers we're doing targeted observations on relatively small scales of a line emission from individual cores to try and understand their density structure, kinematic structure, temperature structure, but really focusing on individual objects that were then fairly well studied across a range of wavelengths. You know, there was some work doing some larger areas, but of course, you know, with 1 pixel, this took time. And so in the middle is showing a region in the Ophiuchus molecular cloud with boxes highlighting some of the regions that I was able to map as part of my thesis with a single pixel in ammonia emission. But it's really been the transition to a multi-pixel array that has allowed us to do maps like the one on the right, which is the Orion A molecular cloud, showing the integral shaped filament and extending down into the south, which was done with the K-band focal plane array and the Green Bank ammonia survey. And so you can see the size scale that we're able to map with a 32 arc second beam and the sensitivity that we're able to reach in a relatively, you know, a relatively good amount of time. So there's been a number of galactic dense gas mapping surveys, and of course I know I'm probably missing a number of them, but I'm focusing a lot on ammonia and N2H plus surveys with ammonia, multiple surveys with the Green Bank telescope like gas, KFPA examinations of young stellar O-star natal environments, Keystone, led by James DeFrancesco, who is absolutely fantastic at coming up with acronyms. So that was pretty funny. And the RAMP survey as well, looking at ammonia in the galactic midplane. And of course, we look at things like ammonia and N2H+, because they're actually preferential tracers of the dense gas, the dense and cold gas in these star-forming environments. And ammonia in particular is really nice because you can get multiple transitions within a narrow frequency range so that you can observe them simultaneously and actually get direct measurements of the gas temperature along with the gas kinematics. And then N2H plus and other lines have been done, some surveys have been done with single dish and telescope arrays. So like the KARMA Large Area Star Formation Survey, Class C, the KARMA Orion Survey, which observed Orion in N2H plus with the KARMA array, but also with the Nobayama telescope. And then as Chaeyu presented earlier, the DISCO survey with Argus, which has focused on initially looking at a small subset of cores within Perseus, but is expanding with the survey starting now into a larger sample of targets. And I just want to also highlight, you know, talks by Peter and Brian Svoboda coming up next with other surveys looking at different regions in the galaxy. So some of the highlights of some of the results coming out of the gas survey, we finished observing several years ago. Our first data release came out in 2017, and since then we've been working on producing science results. And so one of the interesting things that have come out of the survey is because we have fairly wide sensitive maps, we can start to see transitions from the kind of the more turbulent cloud area, still the higher density part of the cloud, but with the ammonia sensitivity, we can see kind of across from core to cloud environments. And so Hope Chen was looking particularly at regions within clouds where you can see a significant drop in the turbulent properties of the gas. So he used gas data to identify this new subset of velocity coherent and very quiescent cores with very low velocity dispersion that he found to be probably at a potentially earlier stage in core evolution because their masses were not large enough to actually be gravitationally unstable. And so he termed these cores droplets. And like I said, proposed that perhaps core formation goes through a process where you form low mass, velocity coherent, quiescent objects that are perhaps initially bounded by pressure, but eventually as they gain mass, will become gravitationally unstable and be more classified as the pre-stellar cores. some of the things that have also come out because we have, high velocity resolution and high sensitivity data is we're really starting to notice that many of our regions have multiple velocity components. And so there's been a lot of work done by multiple current and former graduate students who have been developing line modeling algorithms to identify these multiple velocity components in the ammonia data. And so that's complicated beyond some other molecular line tracers because it does have 18 hyperfine components. So there's been really nice, robust analysis techniques that are being published, and these will also have applications beyond ammonia, and so much of that work is continuing to go forward. But with these maps, we can identify individual emission components from, like I said, the ambient cloud, but also kind of overlaid with the emission from the cores, and that's papers in press and also upcoming. And you can we identify multiple components in cores and filaments. So on the right-hand side, I'm showing you a plot from a paper by Mike Chen, where he's looking at different velocity components in the NGC 1333 region. And so the image is showing you identified filaments in that region with the color scale showing you the change in velocity along the filaments and across the filaments. And so from the spectra, you can see that he's done a really great job of actually disentangling multiple velocity components. And that really allows us to make robust velocity gradient measurements, both along and across filaments, and really accurately measure gas kinematics. So moving into gas and keystone data, this is the MONAR2 region here. And so zooming into a region which was mapped by the Keystone survey in ammonia, what I'm showing in the middle is a plot of the temperature of the gas as measured from the ammonia emission. And on the right is showing you a measurement of the virial parameter for structures identified in the ammonia emission, not just in MONAR2, but in all the Keystone regions. And so by using structure identification techniques, this is a paper by Jared Cowan, who was able to look at the stability of these structures and found a tendency for larger structures to appear bound via this virial analysis. In Keystone, clumps, so the smaller objects, are more likely to be bound by gravity alone, but in the nearby clouds, we found that most cores are actually bound by pressure rather than being gravitationally unstable. So it points to some differences that may be related to the resolution. What are the clumps that we're observing with Keystone versus the cores we're observing with gas? But definitely we see this trend of larger structures tend to be apparently more gravitationally unstable. And I want to highlight too is that I think public survey data means more science. So our gas DR1, our first data release data, was used in multiple papers from non-team authors. And so, and we're also happy to share data beyond the first data release by request. And so pipelines to produce data cubes that can be shared with the community will be really invaluable for Argus 144. And so I was really excited to hear about the archive work that's being done with GBT. All right, so moving beyond ammonia, I want to talk a little bit about what would we observe with Argus 144, how can we build on some of these results? And so I want to talk about dense gas molecular tracers for filament and core kinematics. So once we move into the denser regions within cores, we have this area where the CO freezes out onto dust grains, and that's where our nitrogen-based species, nitrogen-bearing species become abundant. But once you go into the higher density regions in the interiors of the cores, that's when we have more deuterated species become abundant. And so these are really interesting tracers. And just to highlight, in this particular core, the Argus 144 beam at 93 gigahertz is certainly of the right size to actually map the radial profile of some of these species in terms of their abundance, their kinematics, et cetera. So here's a list, not exhaustive, of molecular lines that are available in the 3 millimeter window that would be available to Argus. And so you can see that there's a number of really interesting transitions, low J transitions like N2D plus and N2H plus, obviously not being able to observe together. simultaneously, but a good pair of lines if you wanted to understand both kinematics and chemistry. A lot of these surveys, the mapping of these species is currently very limited. So this is really a place where Argus can make an impact in terms of mapping some of these species. And of course, some lines would probably be better for targeted, deeper maps to get that sensitivity enhancement rather than going wide, as Peter was talking about earlier. And I'd also like to highlight too that there's some complementary chemistry tracers. So not just looking at the dense gas tracers, but looking at things like CH3OH or C3H2, which can highlight regions where you're having maybe low velocity shocks or some more energetic events happening on the edges of cores and looking at that transition. So just to talk really quickly about possible coverage, as was stated earlier, 5 hours estimated to map a 6x6 arc minute region to 0.1 Kelvin and 0.1 kilometers per second. This is actually a pretty good target for lines like deuterated ammonia or N2H+. The gas survey was allotted 245 hours, and with that we covered about 3.7 square degrees in the nearby clouds. So Argus 144 could map about 10% of the highest density gas regions in roughly the same time. Of course, then you could go to smaller regions in higher depth, and to more distant high mass regions would really complement Keystone, I think, by resolving the cluster forming cores and probing those higher density environments that Keystone has already seen in the ammonia. And so this is just, again, showing some of the results that Chaeyu already showed earlier from the DISCO survey. This top panel is ammonia emission from the gas survey in Perseus B1, and then highlighting how we can zoom in to individual cores in N2H+ with Argus. And this little blue box here is showing you kind of what a 6x6 panel would look like. So really, actually kind of well sized to target the higher density regions that we see within the gas clouds. All right, so just to summarize, the large K-band surveys of galactic clouds have led to, kind of new insights into core and filament evolution, and we're still working on many results. The data are driving new analysis techniques, and public data enables more science. So I think Argus 144 will obviously really fill in and expand some of the science we're doing, allow previously unfeasible wide mapping of dense gas tracers, enhance the resolution, and really complement ALMA. So I just want to point out really briefly that, with some of these starless cores and filaments in nearby regions, the sizes of them are such that with ALMA, you would actually resolve out a lot of the emission. And so you really need that single dish telescope to understand the full scale of the structures. And so with that, I will finish and take questions.
Thank you, Rachel. And sorry, I didn't give you your warning, but you only ran over a little bit, so thank you.
Okay.
We do have a question concerning the mapping of the densest regions of gas, for example, N2H+. The question is this require 250 hours per line?
Yeah, so that's a good question. So I think, I want to reiterate what Eric mentioned yesterday, that as it is, Argus is a fantastic, Argus 144 is a fantastic instrument. So probably there are some lines that you could do as pairs that are close enough that you could get within that 600 megahertz window. But yeah, it would be, if you wanted to stick to that sensitivity and the velocity resolution, which you probably do want to do for the local clouds, then yeah, it would be per line. So there might be some trade-off there in terms of figuring out the area you want to cover, the area that would be reasonable to cover, and what kinds of science you want to do, and if you need multiple lines to do that.
And ideally, we would have the ability to cover 5 gigahertz of bandwidth with 50 megahertz small chunks within that 5 gigahertz to get all those lines. But anyway, okay.
Could I chime in on that point?
Sure, Peter.
So with when you multiplex the back end and provide the access to multiple lines at once, it's basically equivalent to multiplying the number of receivers you have by the same factor, as long as you have a good number of bright lines that are mappable. And so I would also encourage whatever effort could be put into broadening the spectrometer to 5 gigahertz or whatever feasible number. At MOPRA, we obviously took this to the nth degree, and it was really amazing. And you get the advantage as well, as was mentioned, that you automatically calibrate all these lines at once, and so there's no cross calibration uncertainty. So yeah, my 2 cents.
No, that's a good 2 cents. I completely agree with that. I think we should look into that, because that would provide powerful capabilities for the instrument. Okay, no other questions, right? Whoops, there was one and it just disappeared. Never mind. I saw a question on the box and maybe somebody answered it already.
I did see it, if you want me to chime in.
Okay, yeah, go ahead and chime in.
It was just a question about the line widths and whether or not you could frequency switch, and yes, you certainly could frequency switch with the lines and the windows that you can use here.
Yeah, the N2H Plus has those multiple features, so you do have to push it a little bit, but Vegas has some modes to do it. But that is something to keep in mind with these complex, with multiple transitions. We need to be able to switch far enough that you can get all the different velocity components. So we need to keep that in mind when we put it, well, anyway, I need to keep that in mind when we put in requirements. And so thank you. So we're going to go ahead and move on to our last speaker of this session.